In this short video, I want to talk about transforming your data. Now, where we want to compare means, for instance, we would use a parametric test, but our data needs to conform to certain standards. There are some assumptions that must be met for the use of parametric tests. And if they don't, we obviously can use non-parametric tests. Sometimes, though, you still want to transform your data. That is where we change every value for a variable based on some function. And the functions that we're going to look at is the log, the logarithm, and the square root transformation of your data. So you might find that in your literature, in the field that you are in, people still make use of data transformations instead of using non-parametric tests. So in case you need to know how to do these data transformations, let's have a look at this video. So in this short notebook, here we go. You can see it's not going to take us too long to get through this. That's all the code and some paragraphs of text there for you. We're going to go through data transformation. So just transforming your data for the use, so that you can use it in parametric tests. Now, I would really advocate for the use of non-parametric tests if your data does not meet the assumptions for the use of a parametric test, but at times data transformation is still used, and I just want to show you how it's done. So we're going to generate some data, as you can see there. So if you download this notebook, it's going to be on GitHub. You can just click on these links here and it'll take you to the appropriate section in the notebook. So we're going to generate our own data. As always, we're going to start with descriptive statistics, just summarizing the data so that we can understand what's going on and visualize it and just see what we can learn from those two steps. We're going to look at the assumptions for the use of parametric tests. Now, we're not going to go through all the assumptions, just the ones that pertain to what we're trying to achieve here with the data transformation. And then we're going to talk about the non-linear transformations that we can do. Now, so those are going to really be the log and the square root transformation, although others are available too. We think of the inverse cosine function transformation and others. And then we're going to compare the means. So let's just get cracking. Well, let me do that. If I just click there on generating data, it takes me to that section in the notebook. So what we're going to do, we're going to have this random variable. It doesn't matter really what it is. But we have our participants in the study divided into two groups, and so in both of those groups we're measuring the exact same variable so that we can compare. Our aim is to compare the means. Is there a difference in mean between the two groups insofar as that variable is concerned? So let's just generate the data. So we're going to just simulate that we have 200 participants in each group. Now these participants, human beings or in some organism, doesn't really matter what it is. We're going to have these two groups. I'm going to call them var group A and var group B for the variable in group A and the variable in group B. So it's the same variable across both. So we're going to just seed the pseudo-random number generator there. I'm just using 17 as the integer there to seed the pseudo-random number generator. Just do that so that every time we run this code, we all get the same pseudo-random numbers. So I'm going to use the random real function there. The random real function, and I want to draw n, there's the n there as my second parameter, and that's 200. So I want to draw 200 random real values from what distribution? Well, from the normal distribution, and the normal distribution with a mean of 10 and a standard deviation of 1. So that's the bell-shaped distribution, and I'm going to draw 200 values from that at random. And then for the second group, I'm just going to add some random noise to that. So look very carefully, the data for group A for this variable is going to be normally distributed, or at least it comes from a normal distribution. But we're going to add this random noise to this. So we take every element of these 200 values from group A, and we add to that 200 values again from a different distribution this time. So we're going to use the chi-square distribution with 5 degrees of freedom. And we're going to draw from that distribution and add that individually to each element in var group A, the values there, and then just subtract 5 again so that we get back roughly to the same sort of mean. So let's run that code. And there we go. You see I've got the semicolons after these lines of code so that we don't see the expression of the execution of the code on the screen. So let's just describe this data, and to do that, we just use summary statistics. I'm going to just create this utility function that I call describe. You can see there, and it's going to take a single argument, v, and that v is going to be a list. So it's going to take a list as an argument, and what I want to do is to return a list. And we use the semicolon equal sign or assignment operator there just for delayed execution. So we're not executing anything here, we're just creating a function. So I'm going to return this list. As you can see, it's inside curly braces there. The mean of the list that is passed to this describe function, the standard deviation, the median, and the interquartile range. So that's just a little utility function. So every time I pass a list object to this describe function, I'm going to get all these results. And let's look at that. So I'm going to call the describe function, and I'm going to map it to, remember this /at that is shorthand for map, the map function. And so I'm going to map my describe function to both of these lists, the var group A and var group B lists that we created there. So I'm going to do the describe function on both, but I'm wrapping that as a first argument in the table form function so that this is neatly printed to the screen as a table. And I'm even going to add some headings to my table. So I'm using the table headings parameter there, and I'm setting the rows to none. So I don't want any names for the rows, these 200 rows of data. But I want mean, standard deviation, median, and interquartile range for the column headers. So let's have a look at that. And there we go. We can see group A and group B there. And we can see the mean 9.9, 10.2, so not very different. Standard deviation, bit of difference there. Median, and the interquartile range, as you can see there. So that's gives us some indication, of course, what's going on here. And the next thing we can really do is just to visualize this data. So here in figure 1, we're going to do a box and whisker chart so that we have a box plot for each of these two groups for this same variable. So I'm passing var group A and var group B, those two lists, as a list. So it's a list of lists there. I want to plot any outliers should they exist. I've given a plot label figure 1 and chart labels so that underneath each of the box plots I have group A and group B. So let's run that. And there we go. So we can clearly see the difference in distribution here as far as group A is concerned. You can see the summary statistics pop up there if you hover over there. But you can see it's normally distributed. But if we look at group B, the measurement of the same variable in group B seems to have a right tail here and quite a few outliers. So we already know just from the information that we have from the summary, but especially the data visualization, that we are not going to meet the assumptions for the use of a parametric test. And that's what we get from data visualization. Another way to do this is just to look at, instead of the box and whisker charts, is just to look at the frequency distribution. So we're going to do a histogram. But what we're going to do is a paired histogram and then a paired smooth histogram, so we can get this idea of the kernel density estimate of the distribution of the values. So let's use the paired histogram function there. I'm passing var group A and var group B, so you see there I'm not passing that as a list of lists, it's just them separately. A plot label and chart labels again. So if we run that, we see group A here on the left-hand side. If I hover over there, we can see it's a frequency distribution, this histogram, how many values appear in those bins. And we can see this long right tail. So, you have to sort of flip it in your head when it's on the right-hand side. So this up, if you have this x-axis here horizontally, this would go out to the right. So this is really positively skewed. And let's do a smooth histogram, same thing as before. And you can now really start seeing this right tail and this sort of a normal distribution to the variable in group A. And just to prove that, let's just have a look at the skewness. And I'm using again shorthand notation, so I'm mapping the function skewness to both of these lists. And you can see almost no skewness for group A, but quite a bit for a positive skewness here for group B. So let's just do something else. I mean, that's visual sort of idea that we are not going to meet the assumptions for the use of parametric tests. And one of those important ones, of course, is the test for normality. And the two things that we can commonly do, of course, is a QQ plot, a quantile plot, and a statistic test to see if we meet the assumption, at least of normality, as far as it comes to the use of parametric tests. So let's use quantile plot. The function there, we're going to go for group A, and we're going to just label this figure 3A, so that just corresponds to the text that I wrote here as notes, if you read this notebook afterwards. And you can see, well, it sort of sticks there for group A, but clearly see that it doesn't that it doesn't for the variable in group B. You clearly see that from this quantile plot that it deviates from this line, which would represent if all our values were on this line, it would represent the fact that it is taken from a population in which the variable is normally distributed. Let's be a bit more precise. If I can use those terms and do a Shapiro-Wilk test for group A, and we're going to return a test data table so that we get both the test statistic and the p-value. And you can see there the null hypothesis for the Shapiro-Wilk test is that the data comes from the samples that you took comes from a population in which that variable is normally distributed. And we see our p-value, if we have an alpha value of 0.05, is not there, and hence we cannot reject the null hypothesis. Let's do the same for group B now, and we see a p-value less than an alpha value of 0.05, or even if we had chosen smaller, 0.01, and we have to reject the null hypothesis and accept the alternate hypothesis, then that states that this data does not come, the samples at least don't come from a population in which the variable is normally distributed. So we fail one of the major tests for the use of a parametric test. So I think this is a good idea just for a little break. I think at least YouTube's going to add a little break here. I'll see you afterwards. So let's carry on and just talk about nonlinear transformations. Now it seems all funny, but you've all seen nonlinear transformations even at school. Y equals x squared. So your input is x, you take a real number x, you input it into this function or mapping, and out pops an element of another set. Remember x, if it's an element of the real numbers, the x-axis is the real number line, and the y-axis is also a real number. So these are two different sets. They happen to be the same set, but you take an element of the one set and you map it to a different element in another set. So if I say y equals x squared, I put in an x from my x-axis real number set, and I out pops a value on the real numbers from the y-axis. So that's what a function is, and that's non-linear. In other words, that line, the curve that you draw for that is not a straight line. So if we talk about single variable calculus, of course, or algebra even, that is a straight line would be the outcome if it's linear. And x squared is definitely not a straight line. Y equals x squared if you plot that. So that's a non-linear transformation. So I do have a plot here. Let's use the list plot, and we're going to use the thread function. So we're going to thread var group A and the log, var group B, I should say, and its log. So what that does is what the thread function does. Remember, I have two lists, and it's going to combine element 1 from the one list with element 1 from the second list into a small little two-element list. And then element 2 with the corresponding element 2, and the element 3 with element 3, because that's what you need here for the list plot. So I'm just going to thread those. And I'm also going to have another one where we have the variables in group B, that group B list, and the square root of that. And some plot legends so that we can have a look at it. So log 10 there, as you can see there, that is the function just to take the log base 10. And remember what the log base 10 function is. It just says 10 to the power what gives me my input value. So log 10, a log base 10 of 10 would be 1, because 10 to the power 1 is 10. And anyway, you can clearly see that these two are not straight lines. They're both curved, so they're both non-linear transformations. In blue here we have log base 10. So for every value that we have in a variable for var group B, and we transform it into its log value, that's what we see on the y-axis, and then let's take the square root we see there in orange at the top. So none of those are linear transformations. So let's do the log transformation. And remember, it doesn't really matter if we take the log or the natural log. It doesn't matter what the base is, because no matter what base you have, there's just a constant difference between the two transformed values. So if I take the natural log, or I take log base 10, or even log base 2, there's just going to be a constant difference in the outcome. So that would be more linear. It would be linear. So it doesn't really matter what you decide your transformation to be. Remember, in mathematics textbooks, you'll see this ln there. That'll be natural log. So that is Euler's number as the base, or the base E. And then just if you see normal log like that there in a textbook, that's log base 10 usually. And for the two corresponding functions, log 10 would be log base 10, and log just like that, well, that would just be log base E. So let's do a list plot. We're going to take the log of B, and then the log base 10 and the normal log. So I just want to show you here that that is indeed, it's a straight line. So whether you take log base E or log base 10, it really doesn't matter. It's a constant multiple difference between the two, a linear difference between the two. So let's do here in 6a and 6b, we're going to show a histogram of the data transformed with both of these, and just draw a histogram of that. And if we look at this, just the log base 10 transformation, it's appearing to be a lot more. Remember that data had a right tail, quite right skewed. It's looking a lot more normally distributed once we do that transformation. And if we do the natural log, same sort of thing, it's a little bit of a tail there. But let's do a QQ plot now of this transformed data. And remember, it wasn't on that normal line at all. But now when we transform these, whether it's just a log base 10 or log base E, as I said, that doesn't really matter. We can see that this data now appears much more normally distributed. And let's do the Shapiro-Wilk test on, they're going to be exactly the same because there's no difference between those two transformations. You can see those QQ plots are exactly, they look exactly the same. And indeed, it doesn't matter what log transformation I do, I get the same p-value back. And that's a p-value from which we can't reject the null hypothesis. So now we can say that this transformed data comes from a population in which the variable is normally distributed, at least the log of that variable. So let's also look at the square root transformation. So we take a histogram here, and we just now take the square root of all of these values. And you see we still have quite a significant positive skewness here. So in this instance for us, the square root's not really going to work. And we tend to use the log transformation for continuous variables and the square root more for ordinal variables, although you have to decide, you have to look at it. What you should do really, of course, is decide on this beforehand. You can't do this and then do a p-value and you say, oh, well, that's not significant for your final test. Oh, let me try another transformation, maybe it will be. You've got to decide that before your data analysis, you've got to stick to that. A couple of things also, one more thing for both of these transformations, remember that the log function and the square root function, those are only going to be defined for positive values. So if your variable contains data point values that are negative, you'll have to shift them first through some linear transformation. In other words, just add a constant to them before you could do these transformations. So just keep that in mind. So let's then compare the means. Let's just have a look at what happens if we take the log of var group A, because we'll have to do that. We can't just take the log of one of the two groups, because then our comparison becomes meaningless. We can't have the values untransformed in the one group and transformed in the other group. That makes no sense. So if we look at that, we see we kind of just about make it. It's 0.08 if we round off there. So we still, as far as the Shapiro-Wilk test is concerned, cannot reject the null hypothesis. So let's take this box and whisker chart now, and we see both of the transformed data. Clearly you can see there for group B that it is now normally distributed, and still to a great extent for group A, and we have that single outlier. So we'll have to check that out as far as the assumptions for the use of parametric tests are concerned, but certainly a single outlier, a t-test would be robust enough not for that to have any influence. So let's just look at the description of the transformed data. So I'm taking the natural log of both now, group A and group B, and we can now report on these transformed data, and you have to have a look in your kind of literature how you report the transformed data and stick to what is commonly done there. So what I wanted to do with this though, with this transformed data, I have a mean and I have a standard deviation, so I can draw two density plots. So probability density function here. So I'm just using PDF normal distribution with the mean and the standard deviation for group A and then again for group B, and we plot those two probability distributions based on these transformed means and standard deviations, and you can clearly see that we're not going to find a statistically significant difference between these two. So let's do a t-test then, a t-test on the log of var group 1 and the log of var group B. Our null hypothesis is that there is no difference between the two. I want to test data table and verify the assumptions for normality. And if we do that, as we can see there, we see a p-value above 0.05. If that's our alpha value, and we can't reject the null hypothesis that there's no difference between these two groups. So let's just, for curiosity's sake, just have a look at, if we just use the t-test on the untransformed data, and I'm going to say verify test assumptions to none. If you set that to all, it's going to give you a little bit of a complaint there saying, well, one of your sets at least does not meet the requirements. I'm just forcing that parameter to none, so we just have a result. And we still see a p-value of more than 0.05. So in the end, this transformation has not changed the outcome of this, and the t-test is robust enough to handle a bit of, shall we say, not upholding all the assumptions for the use of a parametric test. But you can clearly see that there are going to be circumstances in which you are going to get results that might be significant when you should not have used a parametric test, or at least you should have transformed your data. In the end, I just want to just circle back all the way to state that data transformation should not be the first thing that you do so that you can use a parametric test. Think about the non-parametric test, do them. I think that is the appropriate thing to do. And of course here we're comparing two groups to each other, so the test for that would be the Mann-Whitney U test. And we have the Mann-Whitney test function there. We pass the two groups. Now remember, we are comparing the median, but we say that suggests that there's no difference between the group. And again, the property that we're setting there is the test data table. And if we return that, we see our p-value, again, not above 0.05, so we still cannot reject the null hypothesis. So rather stick with that, but in case you have to, you've seen now at least two data transformations to get your data into a form from which you can use parametric tests. I hope you found this video informative. If so, remember, please subscribe to this channel and leave some comments down below. It's nice to interact with a community of people who watch these videos.